I'm looking at 11 o'clock straight up Central Standard Time. Good morning for most, good afternoon for some. Welcome to Pioneer Surface Engineering Academy webinar series. I'm your host, David Jilot, industrial products market leader for Pioneer. I'm again joined by my co-host, Steve Goodsett. Steve's held leadership roles in operations, quality, and of course, product development in his 30 plus years of experience here at Pioneer Metal Finishing. Good morning, Steve.
Hi, Dave.
And certainly good morning again to all of our audience. Important topic today, and just to set up today's webinar a bit, design optimization for plated finishes. Very broad topic, quite frankly, but as we head into the mid-year holiday break, one of the goals we're going to have today with the educational content that we share is to really pique continuous improvement interest and curiosity. So maybe it's a current program that you have that hasn't had a lot of attention because you've always plated it the way you have for many years, and that's just the way you do it. And asking yourself, is that the most optimal way to produce the desired outcome or best performance of your component? Perhaps it's a design under consideration, or an opportunity to extend a warranty cycle on a current product, or even an opportunity to revisit the current plating selection, and perhaps it's over-engineered, and an opportunity to take cost out of the equation. So, certainly we won't have time, Steve, to cover all of the various platings. Quite frankly, there's over 100 in all, and get into the subtle nuances, and we could have probably webinars on each one of them. So again, focusing on broad concepts or performance concepts, whether that be wear, lubricity, cost, or corrosion resistance, quite frankly, and are we thinking about those principles accurately when we're going about our design and selection of plated finishes? So to kind of set up the agenda, Steve, we'll spend a bit of time talking about the overview of plating, what actually goes on at the chemical, physical, molecular level in the process tanks themselves. We'll run through the various steps or the common steps in the plating processes, the immersion chemistry, and what our audience should consider up front, whether it's at design or prior to sending to their outside service provider, their metal finisher. But we're going to spend most of our time today on performance requirements and selecting the appropriate plating system for your desired performance or your desired aesthetics. And we'll round this out with a comparison chart of the most common plating offerings that are available in the market today, or that you're likely to encounter, and leave with a comparison chart that would really kind of steer you in a direction of, am I selecting the right plating system for my current product offering, or are we set up appropriate for the best results? As always, we'll have question and answer at the end, and we'll take 15 minutes to answer all questions. If we don't get to all of them, of course, you should expect us to circle back on a one-off via email direct answer to your question. Okay, well, without further ado, let's get into this. And, as we think about plating, Steve, I certainly have my notion of plating having, whether that was for my formative high school or college years, I always thought of plating as, geez, it's this molten metal bath where you dip your product into the molten metal, it comes out and cools, and you've got a plated finish, kind of like T2 at the end. Obviously, it's far more than that. And take a moment, if you would, to walk the audience through what happens in the various plating steps and at a chemical molecular level, if you would, please.
Okay, well, thanks, Dave, and good morning, everybody. Well, the plating process simply is taking one metal and applying it over the top of another metal. And in the case of our audience, the metal that the plating is going on are your parts. The original plating processes that was invented was the electrolytic process, or most people call it electroplating. And that's been around for a long time. That was created around the turn of the 20th century, the 1900s. And in order to do the electroplating process, you need to have the metal in a liquid state. And that's accomplished by dissolving the metal in a strong acid or alkali solution. And a natural thing that occurs when you dissolve this metal is it takes a plus charge. And this allows us to take this solution now and put the parts into the plating solution. And with a direct current electrical circuit, we can make the part negative, and the positively charged dissolved metal attracts to the negatively charged part, and it's reduced back to a solid state. You do need to use a special type of electricity. It's the direct current. It's not that special. Everybody has direct current in their car and their battery. So you take alternating current, turn it into direct current. Then later on, as time went on, over the course of time, the autolytic process was developed. Many people call this the Electroless Nickel process. Instead of using a rectifier to provide the energy and have that be the catalyst to reduce the positively charged ions, a chemical is used for that process. And then as we progress on, in the 1970s, a gas state process was created, the ion deposition process, sometimes called PVD, physical vapor deposition, IVD, thin film processes. So back to the original plating process, the electrolytic or the electroplating process, a variety of metals can be used for this process, anything from zinc, copper, brass, you name it. Nickel, chrome, precious metals, palladium, gold, silver. One of the downsides, though, of this process is that because we're using electricity to create the plating, electricity has the tendency to follow the path of least resistance. So when we get into low current areas or recessed areas on the parts, it's hard to get the uniform plating to occur. So sometimes people call it the dog bone effect. Down in the recessed areas, you don't get as much plating. In the high current areas, then you get heavier thicknesses. Most of the different metals are limited to about 2,000 thickness of plating. The advent of the Electroless Nickel process was very exciting. This was a chemical process, as I mentioned. Now the electricity part of it is taken out of the equation, and very tight tolerances can be attained, plus or minus 1/10,000th of an inch. This is assuming that you can get good solution flow. Even the inside of parts can be plated. And theoretically, the plating thickness is unlimited. So for heavy wear, heavy corrosion applications, up to 5,000ths of coating can be applied practically. Very good for salvage operations also.
So Steve, now that we've established really a foundation of sorts on the plating process itself, getting into more of the material or the substance of the actual process and the physical steps that parts would go through, let's roll this forward just a little bit and provide some upfront considerations for the audience. I'll always take the opportunity to put a PSA out there for packaging, whether that's packing to protect, incoming to your metal finisher, or packing to protect on the outward bound side, or avoiding transfer of coolants, making sure packaging is clean. You spend all this money and time manufacturing a product, and the mistake is sometimes a short-sighted view of packaging, or avoiding the thought of packaging and packing product properly, incoming and outgoing from your finisher. So always want to consider different packaging strategies, also to reduce time from a handling perspective, and that's of course cost. But let's focus then on the surface texture, or the pre-treatment from a mechanical perspective of the substrate. And really what we have here, not a lot unlike anodize or even paint or powder, where a very smooth or polished surface will produce a high shine result after plating. Just the same, a roughened surface, whether you're using blasting or some sort of straight line sanding or tumbling effect, or even a chemical etch, will produce a matte finish. So wanting to keep those in mind, obviously with an electrolytic plating process, you have more of a deposition at an uneven rate, and so your surface texture will become more muted versus electrolysis. So keep that in mind as well. But that's really how you would control luster or shine versus, say, a matte finish, is mainly in the mechanical pre-treatment of the substrate. Also worth considering here is the masking requirements. In the photos at right, you can see some various masking strategies, tape and paint. Masking is especially predominant with electrolytic processes where you have a higher variance of plating thickness. So think finer, tighter tolerance areas or even threads, blind holes. You're likely to have to mask those in the electrolytic plating process, whereas an electroless process, as long as you're getting good chemical flow, you will get, again, plus or minus 1/10,000th of an inch plating thickness. So oftentimes you're able to avoid the costly masking from an upfront perspective with electroless processes. Also worth noting here is the tooling selection, and really two main strategies at work. Fixated tooling strategy, similar to say an anodized process where you're racking individual pieces, typically with mild steel or stainless, even copper wire for tooling material. And then of course there's the barrel or bulk barrel process, which drives, of course, cost efficiencies, high volume production, but really limited to a smaller envelope and type of parts, parts that don't have blind holes or deep recesses, or even flat parts that lend themselves to nesting or, of course, part-to-part damage with heavier parts and sharp edges. So want to be cautious there. Of course, barrel plating versus rack plating going to be apples to oranges with price. So if you're after a very cosmetic finish, a consistent finish, consistent thicknesses, you're going to want to consider rack plating versus barrel. Doesn't mean you're dead in the water with barrel plating, but certainly more risk involved there. Okay, Steve, so we've got the product set up. We're ready to start exposing it to the chemical immersion processes. Walk our audience through what happens in these various steps and what they should consider.
Yes, so regardless if it's going to be electroplating or electroless plating, you have to get the parts pre-treated properly. They have to be clean, oxide-free, and the metal finisher needs to know whether it was a hardened material incoming, and really important is what alloy it is. For the different base metal alloys of the parts, there's two basic streams or lines for pre-treatment. The non-aluminum materials would be your ferrous alloys, whether that's a mild steel, a cast iron, a stainless steel, a leaded steel. And then there's also the copper-based alloys, the brasses, beryllium, copper, things of those nature. And then you have your aluminum materials, and that has a whole different type of pre-treatment process. When you're going to do your non-aluminum materials, you're going to use a high-temperature alkaline cleaner to soak off oils, buffing compounds, any kind of soils. And then we go to another step where we're going to use electricity and really deep clean that surface. Once we've got all the dirt off and the oils off of the part, then we would attack the oxides and we would use different acid solutions. Sometimes this is referred to as pickling. Now, some of the base metals that are more passive, like a stainless steel, need a little bit of a push, a little bit of a oomph, and a thin layer of electroplating would be applied. In this case, it would be either nickel or copper. And then for the aluminum materials, we're going to use a little lower temperature, milder cleaner, so we don't attack the aluminum. Again, we need to do some deep cleaning. We'll do a chemical etching process. And with aluminum, we've got to add a few more steps here. We do a zincate conversion to protect the aluminum, and then a nickel alkaline strike. At this point, the parts are ready to go in the plating baths. One of the most important things, though, in this process that can't be overlooked is the purity of the rinses and the proper dwell times in these rinses to make sure we're not contaminating the different solutions or trapping chemical residue in blind areas, recesses. So it's not only controlling the chemistry, but it's also understanding which chemicals need to be used and then following through at a proper process.
Yeah, so Steve, if I really had to sum that up, I mean, cleaning, pre-treatment, making sure we don't have any disruptions at the surface for the positively charged ions of metal to be deposited on and form a good, strong bond and really drive the adhesion process. So yep. Pre-treatment cleaning and avoiding any sort of embedded material, of course, as you mentioned, or dried coolant, those are always immediate red flags for any metal finisher, quite frankly.
Yep. So once we're sure that the parts are cleaned and we're not going to have bare spots or blisters or poor adhesion overall, when we're in the plating tanks, this is a really critical area for the line operator and the chemistry team not only to make sure all the variables are controlled tightly, but we understand the driving factors on the thickness of the plating. For the electrolytic process, it's the amount of electricity that we're applying and how long we're in the bath. And for the electroless process, what's the activity of the bath? And again, how long are we in the bath? And then after we come out of the plating tank, that's where the operators are going to be doing their in-process checking to ensure the process is in control and we're getting the desired thickness. After parts have been plated, we have to take into account that the parts might have been hardened incoming. Hard materials are, anything that's hard is going to be more brittle, easier for it to break or crack. During the plating process, hydrogen gas is created, and whether it's in the electrocleaning, the pickling process, or the plating bath itself. And what the plater needs to do is ensure they're driving any of that absorbed hydrogen back out of the base metal so that we don't cause extra brittle state to this hard metal. And it can also affect the adhesion. So adhesion baking might be not only for hard metals, but certain alloys like aluminum require an adhesion bake. In the past, when a process like Electroless Nickel, which is already hard, wanted to be made even harder, a hardness bake was applied. But the downside of doing the hardness baking on the plating is it took away some of the other great attributes of Electroless Nickel, such as high lubricity and good corrosion protection. They have invented new versions of Electroless Nickel, like the low phos process that's naturally over 60 Rockwell hardness. At Pioneer, we don't feel that hardness baking is a good thing to do for the Electroless Nickel process. Once the parts have been through the entire process, that's where the final inspection is being done. Thickness verification for all the different plating processes can be done in real time, either dimensionally with a micrometer or with X-ray equipment. And then if we want to really, get down to the down and dirty on how accurate the thickness is, a microscopic examination can be done. But now, unfortunately, this can't be done in real time. It takes a few hours to do a microscopic examination. There's also adhesion testing that's available to do either on the parts themselves or a referee sample, like a panel, whether that's bending the panel or doing impact punches on it to ensure the plating is holding up, doesn't pop off. And for the products that require solderability, there's testing for that too available.
Yeah, so Steve, really just, a myriad of tests, and obviously spec dependent. Specs will have all sorts of tests, whether there's stain tests or even chemical exposure tests. You could could have a whole webinar on post-process testing or specs. Yep. and what that presents. Okay, so now that we've kind of set the outline of the plating process itself and the various considerations prior to plating that we should have in mind, we really get into the meat of the presentation, and I want to drive this point home. The key factors that would drive you to select a particular plating system versus another, and desired outcomes. So thinking of your applications and what environment they're in, if they're in maybe an outdoor environment or a marine environment or even a metal-to-metal contact interface or light transfer. This is really where we get into, again, selecting the appropriate product for your application. So Steve, walk us through the most common attributes that we'd be after at the design phase and looking to solve those issues.
Well, wear resistance. There's platings that are much harder than base metals that are used to manufacture parts. One of the most critical attributes you'd be looking for is how hard is the plating. Unfortunately, you can't use standard Rockwell testing to test the plating, so you do have to do micro sections and do micro hardness. The different types of micro hardness testing are the Vickers and the Nuke type testing. And the types of platings that do a really good job are the low phos Electroless Nickel, hard chrome plating, the PVD, co-deposit type platings. And then we move on to corrosion resistance. The different types of corrosion resistant coatings that are out there are the high phos Electroless Nickel. When we're at 1,000ths of
thousands of thickness, Steve. Yeah. So thousands of thickness.
Yep.
And
so 1,000ths of thickness is a pretty good range to ensure for high phosphoelectroless nickel that you're getting 1,000 hours of salt spray. There's also the zinc platings that are out there that offer sacrificial protection. And then there's different types of testing to see how good the corrosion protection is, such as humidity testing, and then special customized testing, such as cycle testing. Your product might need to hold up to high pHs, low pHs, and there's special testing that's out there for those types of validation. You might be looking for maximum lubricity. The one way to check the lubricity of a coating is the coefficient of friction. The lower the value of the coefficient of friction, the slipperier the part is. When you combine lubricity and hardness, that's where you see your best wear resistance. The advent of the Electroless nickel coatings where we can add the PTFE and combine the slipperiness of the PTFE with the hardness of the Electroless nickel provides a very good coating.
Yeah, so really the tribological impact or setup, if you will, Steve, between a hardened coating but also the lubricity factor and how those interface or work in the same principle or same direction, especially for high cycle, light load, transfer type applications.
Yep. And then you may be looking for, the conductivity of the plating. Many times people are going to be using copper or aluminum as their very conductive base metals for the products that need to conduct electricity. Unfortunately, those are reactive metals, they're soft metals. If you're in an application where there's going to be wear, you might be looking at adding a hard gold. Not only does the gold provide wear resistance, it's a very passive material and it'll protect the base metal from oxidizing. Tin is a very good conductor that can be applied for enhancing the conductivity of the base metal. Nickel does a neutral job. It can protect the base metal from corrosion, enhance wear, and not impede the conductivity. Silver is also a great plating process to enhance the conductivity of the base metal. But overall, there's other considerations such as preserving the dimensions of the part. As you mentioned, there's the masking, but again, Electroless nickel does a great job here in that it's going to provide a very uniform finish. And then the ductility of the coating, if the part's going to be flexed, if there's any inflection, it's important to have a coating that can stand up to that. It can be stressed and not break. And again, plating such as tin does a very good job for solderability. Nickel platings, both Electroless and electrolytic, do a great job of EMI shielding.
Yeah, really a whole host of, I'll say, miscellaneous or specialty performance variables that various platings can offer. Don't have time to get into all of them, but certainly some of the more common ones here listed. Rolling this forward then, Steve, talking a bit about aesthetics, and you think about plating, and there's really a subset of plating that is aesthetically driven. Think your gold plating, your jewelries, your high cosmetic applications, mainly consumer products, quite frankly. But the reality is performance or functional performance is the primary driver of any sort of plating demand, most commonly. And it's important to note, again, we mentioned it earlier, the appearance factor. So brilliant shine or luster is created by polishing or pretreatment of the base metal to create a smooth surface, as well as matte being a matte appearance being created by roughening the surface. So typically the ability to control reflectivity is most common with aesthetics relative to plating. It's also important to note there's very limited color options available for plated finishes. Of course, there's black applications, black zinc, black nickel, black chrome, but it's very common with those as well because platings are barrier coatings by and large, and so there's really not a good adhesion surface or roughened surface for those particular, typically organic colorants to adhere to. So any sort of dyeing or colorant along with a plating, unless it's electro-deposited with the plating, is going to be more superficial or surface-oriented and not as durable or wear scratch resistant. So keep that in mind. And that's oftentimes, why you see, plated finishes are going to be metallic in nature. That's just the nature of it. I'll also take this opportunity to point out again the barrel plating process here relative to aesthetics. Not recommended, quite frankly. Now, there are certain applications, small, say, commodity type shapes of parts that you can get away with barrel plating and still produce a cosmetic finish. There's really no way to predict where touch marks or any sort of potential shadowing or shielding of the electric current could take place. Obviously, have less of that in the electrolysis process, but still a high propensity for staining, a high propensity of having touch marks in places or critical surfaces that they're not meant to be. And of course, if you have any sort of blind holes or recessed areas where solution's not going to drain out, you're really at the mercy of the barrel plate process, and it's not recommended. A bit of process chemistry splashed over an entire load of parts, you probably lose half the parts in terms of fallout and requiring rework. So again, think barrel plating as really your cost-effective way for functional performance coatings on a select shape or style of part. So to round this out, we've got a series of charts, and really to summarize our discussion today on the most common platings that we see in industry, quite frankly, that surveys, whether it be products finishing or what have you, have indicated are most commonly in demand. Many of them offered at Pioneer Metal Finishing, not all of them, but the intent here is to give you not only this matrix, but also the performance functions or performance variables that are most common in design or in intended outcomes, and really begin to set up the structure for comparison. So you may have an opportunity today where you're looking at a program and, geez, there's tight dimensions and you want the part to look nice, maybe like a nickel chrome, not as much concerned about corrosion protection. And nickel chrome would seem to be the most obvious, a brilliant, nice reflective shine, but how do you protect your dimensions? You're best not masking those because you've added costs there. Perhaps a low-phos electroless nickel or even a polished component with low-phos electroless nickel would suffice not only your dimensional demand, but also the brilliance, the shine, the aesthetics. Perhaps there's a application you have that is cost sensitive, and it's an interior application, and today maybe you're applying a thin layer of electroless nickel or even a nickel chrome or a zinc nickel, and geez, that might be overkill. And comparing that versus, say, just a down and dirty zinc plating process. So really designed to get the audience to think about the various concepts at work here as you go about either designing new programs or revisiting from a continuous improvement perspective your existing portfolio. And then just really to break this down, I know that previous chart was a bit complex in terms of all the different variables, but we have a juxtaposed chart here, basically a spider chart of the two most common attributes preferred in plating, that being wear and corrosion. So we've segregated the coatings by their main attributes. If coating is considered a wear coating, it's in that bucket, obviously corrosion in the other bucket. And then also weighed in, I'll call it the secondary attributes and where these coatings would fall on a scale of 1 to 5. So again, designed to get you thinking about the concepts of your plating systems. And again, every application being different, and we're always happy to answer any questions you might have about specific applications, specific coatings. Will this work? What would we recommend here or there? So of course, much more information to be found at the Surface Engineering Academy homepage. You can find that on our website, either through the link here or at the top of our website, a link directly to the Surface Engineering Academy. So white papers to be found there, short video segments, of course, product handbooks, product data sheets, etc. So really would invite you to check that out. And if there's any more questions with some of the material you see there, always happy to answer those on a one-off basis. But that really leads us to the conclusion of today's content and into our question and answer session. So again, the Q&A icon at the bottom of your screen allows you to pose direct questions to Steve and I via the chat feature, and we'll go ahead and get started. I see first question in, Steve, can you describe the conductivity attributes with Electroless Nickel?
Electroless nickel is pretty much considered neutral when it comes to conductivity versus like a tin or a silver plating, which would enhance the conductivity of the base metal. It wouldn't interfere with the conductivity of the base metal.
And second question, thank you, Klaus. What's the price difference between Electroless Nickel and zinc plating?
So David, I would think that in general, you have to look at a value there where zinc plating, mil square foot cost might be lower, but ultimately it has disadvantages when it comes to coverage, corrosion protection, wear. So it really goes back to a value analysis.
Yeah,
maybe I think would know better in a dollar to dollar thing, David.
Yeah, I would say, you know, when I see these questions, and I get them quite frequently, I typically say zinc on average, maybe 15 to say 30%, just depending on the application, the degree of difficulty of the program or the part shape and complexity. Certainly zinc is going to be more cost competitive, but to your point, Steve, from a function perspective, even corrosion perspective, you know, say a 5/10 or even a mil thick layer of zinc is going to perform well, but even a 2 to 3, maybe 4/10 thick medium phos or high phos coating of Electroless Nickel, certainly high phos, would perform as good, if not better. And again, that difference in coating thickness can sometimes make up for the difference in price. So, but I would say apples to apples zinc, yeah, it's going to be probably in the 15, maybe 20% range, more cost competitive.
Yep. We've got a question from Corey here. How would a co-deposited PTFE Electroless Nickel perform versus standard PTFE coatings? Well, the advantage of the Electroless Nickel with the co-deposited PTFE is that it's going to be much harder, much better wear resistance, and most PTFE coatings are going to be applied either with a spray process, and so the uniformity is going to be just like if you're spray painting something. It's going to be very difficult to get uniform coating. So the co-deposited PTFE can have 4 to 5 times the wear resistance and the better overall uniform coverage. And now you also have the chemical resistance and the hardness, a lot of much better attributes than standard PTFE alone.
Next question coming in, Steve. Respect to tooling, how are the parts in the tank racked to avoid spots where the part is held? So rack marks, or how is it possible to not see a racking point on a part? And I think there's some good nuggets here with respect to electrolytic versus electroless plating and what we're able to do with rack marks.
Yep. Well, many times if the rack mark is of concern, we can do things from an engineering standpoint. Maybe a hole can be put in a part if it's a heavy part to bolt it on. One of the big advantages for Electroless Nickel, again, is the fact that because we don't need that tight contact like with anodizing, you can have the part moving on the rack and have almost invisible rack marks with the Electroless Nickel process. But generally, you're going to be using a combination of a hook and make sure that the least amount of contact is there, or when it's in a case of a clip, making sure that not only is it the least amount of contact, but if there's an area on the part where a rack mark would be a real issue, that we understand that before we do the design of the racking.
Yeah, typically with with Electroless Nickel, unless you're having to do some sort of pretreatment strike, which would be electrolytically deposited, you're able to drive, like you said, almost a phantom rack mark scenario. Additional question I'll ask here, Steve, relative to post-process bake, and we covered it briefly in the presentation. But whether it's a post-process bake for hardness or adhesion, we always want to be sensitive not only of the time and the temperature for the sake of the coating, but also the base substrate, and that we're not impacting the structure of the underlying metal or substrate. So I guess the question I'd have that I've often been asked, with various opportunities is, how does post-process baking for hardness actually impact the plating? From whether it's you reference corrosion and lubricity reductions, what actually happens there?
Well, let's talk in terms of electroless nickel plating. When you do post-baking, if you do it for hydrogen embrittlement, it's at a temperature of 400 degrees and it won't have any negative impact on the plating. And if it's for adhesion, it's either going to be 400 degrees for many alloys. Aluminum, it's only at 250 degrees Fahrenheit. When we look at hardness baking, we have to get up over 600 degrees. And electroless nickel is an alloy of nickel and phosphorus, and it's a very uniform layer, crystalline type layer. And when you get up to the level where you're hardening the plating, you actually micro crack it and you precipitate the phosphorus out of the coating. Both of these things reduce the lubricity and dramatically reduce the natural corrosion resistance of the plating.
Yeah,
and again, as I mentioned, I'm sorry, Dave. As I mentioned,
you really want to be careful with hardness bakes. The only reason to ever implement a hardness bake is just if you had pure wear resistance as the desired outcome of your plating system.
Yep.
Okay, next question coming in. What is the process for determining the optimized plating solution? Is it possible to create a custom solution that may combine processes for a unique solution? This is at the heart, and one of the challenges in the presentation build that Steve and I had was looking at all the different variables that are available in different plating processes and how to build kind of the hybrid, if you will. I think there's some opportunities to be done. We see the different co-deposits, whether those are Electroless Nickel. Certainly PVD offers that level of flexibility as well, with whether it be additives for lubricity, for hardness, or different chemical properties for corrosion resistance. So you definitely gain more flexibility in the more modern engineered coatings such as PVD. But of course, there's a cost factor to be shared there as well. So Steve, I don't know, any other input on that particular question?
Well, as we showed with the charts, the engineering and understanding what attributes the plating should be offering for the customer to improve the performance of their parts needs to be taken into account. There is opportunities, though, to do combinations of platings. We are right now developing new versions of Electroless Nickel where we're combining the different types of phosphorus contents in different layers to combine those different properties. There's even opportunities that we're researching at this time right now to add antimicrobial impact to plating processes. So it really does go back to what does the market say is needed out there, and we're always looking for improvements, continuous improvement of the processes.
Yeah, or likewise the need or reason, the market opportunity to develop something new along those lines, whether it's a cutting edge PVD type coating or some sort of nanotechnology coating where you have much more flexibility with some of those variables. But it's, if you look at the old plating technology, and I say old, I mean the traditional plating technology that pervades through much of manufacturing today, typically hardness and corrosion resistance operate in conflict with each other. Typically to drive corrosion resistance, you're adding co-deposited, say, phosphorus with nickel phosphorus, Electroless Nickel. Well, the phosphorus is great for corrosion resistance, but it softens the coating and so therefore has an impact on wear. So all things to consider, but to Steve's point, yes, some new technology being developed now, and certainly opportunities to partner and to work with opportunities in the marketplace. Unfortunately, sometimes the spec requirements change at a much slower rate than, say, the available technology or capability of new coatings. And so you're kind of limited to, well, this is what we've always done, and change happens at a much slower rate from a specification standpoint.
Mm-hmm. I guess just overall, when you're going to get involved in a project, it is critical to understand why you would be doing plating processes and get your plater involved early on in the process, especially if you've got some ability to choose the plating type and the different attributes of the plating type, thickness, so forth, the base metal that's going to be chosen, things that are important to the plater to make sure they can be successful for you. You, for example, might feel that you need wear resistance and you go ahead and harden your material, and ultimately that required more work for the plater versus just getting a hard plating on the surface of the part. So it's just important that if you have the ability to choose the plating process, get your plater involved as early as possible in the engineering phase.
Yeah, that's a good point, Steve, especially around material hardness or even incoming material and the latency of some of the incoming materials. I think of stainless and some of the challenges those would present, but and then of course the availability from a strike perspective to promote proper adhesion and all of the different intricate pre-process steps that can be required for success there. So yeah, to your point, having a strong mutual two-way open relationship with your metal finisher can really help avoid a lot of those pitfalls.
It's the best way to create a robust process at the lowest cost.
Okay, well, it looks like most of the remaining attendees have responded and given us great feedback. Appreciate that. Appreciate everyone taking time out of their busy days to join us.
Yeah, thank you very much, everybody.
All right, well, we'll go ahead and close the webinar. Appreciate everybody. Our next webinar coming up will be on automotive finishes, automotive applications, specifically related to adhesives. We'll also touch on some other ancillary coatings related to automotive. Look for more promotion, more notes on whether that's email or LinkedIn. The ability to always to sign up at our Surface Engineering Academy. That'll take place mid-July. But until then, of course, enjoy your weekend, enjoy the 4th of July Independence holiday, and thanks everyone again for joining.